Paul's an industry veteran, having worked in DSL and now more recently in fiber PON, and I think fiber everywhere. So let's get this going.
Thank you. Thank you for the introduction. Welcome all. So I'm located in Antwerp. What you see here is what we call the MAS, the Museum at the River, Museum aan de Stroom in Dutch. It's near the center of Antwerp, and it's also near the port of Antwerp. And what you see on the background is what you typically see in Antwerp and other big cities, I expect, all around the world. And you see many multi-dwelling units, many apartment buildings. And this presentation is about bringing broadband to multi-dwelling units. Let's start with looking at the context. So fiber broadband, we see different observations. We see different trends. First of all, fiber is booming. There is an enormous amount of fiber deployed and being deployed, and we are marching towards 1 billion fiber subscribers next year. If we are looking at the access landscape, a broadband access landscape, then we see the vast majority being fiber today. We see that DSL is gradually decreasing. We see that cable modems, it's more or less stable, and fixed wireless access is gradually increasing. And fixed wireless access can be used as a complement to fiber in certain regions, but it can also be used as a first entry till there is sufficient take rate of the service before the operator starts with fiber deployment and fiber investment. And what I'm saying here, I think, is pretty much in line with what Roland Montaigne said yesterday, Roland from iDate, first presentation yesterday. So that's the first trend. Second trend that we see in the market of broadband access, that is speeds are booming. And you see here 1 gig, 10 gig, 25 gig. So most operators started with, if not all, with GPON deployment. We see that today operators are, or some operators already are upgrading their networks to XGS-PON for delivering 10 gigabit symmetric services. And there is also 25 gig PON available. Yesterday you heard a lot about 50 gig. Now let's do a quick reality check. 50 gig PON is not available today. It's not commercially available. 25 gig PON is, Nokia is having a 25 gig PON product. And I did a check yesterday evening. I looked at the MSA website, 25GS, so Gigabit Symmetric MSA website. This is an alliance of industry players that promote and accelerate 25 gig PON, and there are currently over 60 members. If you look at the membership of the 25 gig PON, then you will see that you have a very nice mix there. There are operators, including tier 1 operators. There are, of course, system vendors, Nokia being one of them, and the main driving force behind this. But we also see ONT, ONU suppliers, a good variety of well-established ONU suppliers. By the way, Nokia is also selling ONUs. But it's good that we see that in this community we have a very solid industry base. You also see chipset suppliers, vendors of coexistence element. So the whole ecosystem of 25 gig is in place today. What is not the case yet, I think, for 50 gig. Of course, 50 gig will come. Already in 21, Proximus announced that they activated as first operator a 25 gig line in their live network. And I think that if you look at the situation today where we are with 50 gig, it's probably where we were with 25 gig 3 years ago. And in October last year, Google Fiber announced that they started deploying Nokia 25 gig for offering 20 gig services to residential users. But that was a bit a side note. So we said second observation, second trend is speeds are booming. You see there also at the bottom, these are numbers from last year. So we already saw worldwide over 450 gigabit networks, even 90 multi-gigabit networks, and 100 million gigabit subscribers worldwide. Another important observation is that fiber speeds can be monetized, and that is of course key, because deploying fiber requires big investments, and operators expect revenues, a return from these investments. Operators expect it, and the market is expecting that as well. And we see that, for instance, that more and more gigabit and gigabit plus offers are being made, and that the number of lower speed tiers is decreasing. And fiber is also a very green technology if you compare it with alternatives for broadband access. And important is also, if you go at the higher flavors, the higher speed flavors, that you can use the fiber not only for the residential access, but it's also perfectly suited for serving the industry, the enterprises. It's enabling smart cities, and you can use it for mobile transport. So all that makes that the total cost of ownership of 25 gig PON is very attractive, and it's a very green way, power efficient way to deliver the services to the market. So that makes that today, and I think that's clear, fiber is the first choice when subscribers can be reached economically, but we need a solution to extend the fiber in the hard-to-fiberize multi-dwelling units. Because indeed there may be challenges in these brownfield MDU deployments for fiber to the home rollout. And this for different reasons. First of all, often there is no tenant permission for doing the necessary construction work inside the building. Secondly, often cable routing in these older buildings can be difficult. In many cases also the in-building infrastructure is owned by the building owner and not by the operator. So what makes it less attractive to do the investment to fiberize the building? There may be legal and administrative issues, and there is also no common solution for all buildings. Basically, all buildings are different architectures. What works in one building may not be a suitable solution for another building. And was also indicated yesterday, also by Roland Montaigne, in many countries, the MDU segment, it's an important segment if you look at the households. So operators are faced with a dilemma for delivering gigabit services in multi-dwelling units that are difficult to fiberize. And there we see different approaches in the market. On the left, these are operators that say, I do partial coverage with FTTH. I will connect all easy to fiberize MDUs. And that basically means that you offer FTTH where it's practical, but you skip the difficult MDUs. So you leave part of the market, part of your customer base unserved. That means, of course, that the number of customers connected can be significantly less than the number of homes passed. It also means much less revenues, and even worse, you risk to lose customers to competition churn. The middle approach are operators that say we are very strict on FTTH, we bring the fiber to the end user, whatever it takes, whatever it costs. What also means this results in a much longer time to market, in extra investments, in delayed revenues, and in some cases it will even not be possible, so still making that some users do not get the benefit of the fiber speed. And then the third approach on the right, that's a more pragmatic approach. That is where you say, let's bring fiber to the MDUs and within the MDUs wherever feasible, but complement it with what we call gigabit connect where it's difficult, so for the remaining MDUs, by leveraging the existing infrastructure in the building, whether it's twisted pair or copper. And that means that the operator is delivering gigabit speeds and fiber experience to all customers, whether they are on fiber, on copper, or on twisted pair. And it gives you a much quicker time to market and a quicker return and revenue. So Gigabit Connect, what are the benefits for the operator? First of all, the solution that we are offering, it's a very scalable solution. It's also a very flexible solution. It works over twisted pair. There we make use of G-Fast technology. And it works over coax. There we make use of MoCA technology. And MoCA can be used in coexistence with legacy TV services or with DOCSIS. We offer a unified management, whether it's for PON users, MoCA users, G-Fast users. We have zero-touch provisioning. And for the end user, it means that they get gigabit services in downstream and upstream if they are connected over G-Fast. With MoCA, they even get 2 gigabit per second in both directions and in all cases, low latency. So that means with this, we convert homes passed to homes connected. And for the operator, it meets the objective to maximize their access infrastructure investments. To make it a bit concrete, these are some pictures of G-Fast deployment in MDUs. Later this morning, Helge Tienen will give a presentation with examples of MoCA deployment. So what you see on the left, that's a traditional copper cabinet. So where you had the MDF blocks, there was the twisted pair going to the end users at one side and going to the central office or the VDSL cabinet at the other side. This cabinet has been modified to include fiber distribution. So you see there an ODF, optical distribution frame, and there are also splitters in the cabinet. And thus from this cabinet, you have point-to-point fibers to FTTH users in that region, and you also have point-to-point fibers to G-Fast DBUs in certain MDUs. So this is a very nice example of an area. So the cabinet serves a dual purpose. It was traditionally the users were getting service over DSL. There are still some of these customers remaining, but a large portion of these users are getting fiber service or with pure FTTH or with G-Fast. The buildings that you see in the middle, these are examples of buildings that get gigabit services making use of G-Fast technology. So it's like a small village, a community. And then on the right, you see an example of a G-Fast installation in one of these buildings. So you see there an MDU building closet with on the top left, the G-Fast DPU. Top right, you see the connection box with the in-house twisted pair. In the middle, there is an outside plant cable interface protection block. It contains primary protections. It was already in place. And then at the bottom, you see it's a new box that was installed. That is the distribution PON interface from the splitter. So basically, that's where the fiber coming from the street cabinet on the left enters and where you patch it to the fiber that goes, that feeds the G-Fast DPU. Let's now have a look under the hood. What is the technology that we use under the hood? Two use cases, twisted pair and coax. Let's start with twisted pair. So for twisted pair, there are basically two options. And there is G-Fast and G.hn technology. Both have been standardized by the ITU. If we compare both technologies, both can do point-to-point communication. Point-to-multipoint is not applicable over twisted pair. Both use a very similar spectrum, roughly 200 megahertz at the low end of the spectrum, but G-Fast a little bit more. In terms of achievable bit rates, G-Fast can achieve 2 gigabit per second aggregate and 1.7, 1.8 in each direction. G.hn gives up to 1.7 gigabit per second and 1.5 gigabit per second in both directions. And very important last point, only G-Fast is capable of giving sustained rates under crosstalk conditions. Now, crosstalk conditions, that is very common for twisted pair. You know, these twisted pair come together in bundles, in cables, and there is leakage between the pairs. We know that since the old days of ADSL. And with ADSL, that was acceptable. With VDSL, we introduced vectoring to cancel the crosstalk, and with G-Fast, vectoring is even an inherent part of the G-Fast standard and of the G-Fast technology. It's always there, always enabled. And already at the Broadband World Forum 2013, 11 years ago, we made a presentation where we did early test with G.fast. By the way, at the time, G.fast chipsets were not yet available on the market, but we used the prototype from Nokia Bell Labs. And we already demonstrated the importance of the crosstalk cancellation. You see that there is an enormous drop in bitrate if you activate multiple pairs in the same cable, and that you can overcome this drop by cancelling the crosstalk with vectoring. And we recently, not recently, last year, we repeated these tests. We had a setup with a DPU. We activated 4 lines over twisted pair, 100 meters, 0.4 millimeter. And we took a G.fast DPU. We sent simultaneous traffic to 4 users. When you activated 1 line, we had a gigabit per second. When we activate all 4 lines, we had still 950 megabit per second, so very close to the single line performance. And then we repeated the test with G.hn. Again, with a single line, we had close to gigabit per second, but when we activated the 4 lines, bitrate dropped to less than half. So our conclusion is G.fast gives you the best bit rates, but it is also the only technology that can guarantee sustained rates under crosstalk conditions that are very common on twisted pair. And 2 important components of G.fast, and I'm telling nothing new here, that is vectoring on the left side, and in fact I already referred to the vectoring, and the left picture is a nice illustration of it. It's an old measurement, it's still G.fast 106 megahertz, but if you would repeat that with 212, it would only be more pronounced. So we had here a cable with distributed customers at different loop lengths, and when you activate them all without the vectoring, you get the brown dots at the bottom. When you activate 1 line at a time, you get the orange dots at the top. So you see, and then by activating the vectoring, you get the blue dots. So you basically, in this case, triple performance. And as you can see, the vector rates are very close to single line rates as it should be. The other component, another key component here is what is called CDTA when applied over twisted pair, coordinated dynamic time assignment. Basically what it means, with G.fast, you have a certain aggregate capacity, and that capacity is to be used for the up and the downstream transmission. And that's and you need to decide how you split it in upstream and downstream, and that's done in a very dynamic way based on traffic demand. And you see here an example where first you are sending some data in downstream, and then you switch to the upstream, and almost instantaneously you see that this split is updated automatically by the system. So first you get a gigabit per second in downstream, and then you get a gigabit per second in upstream, although maybe the aggregate capacity was only 1.3 gigabit per second. By the way, also G.hn needs to do something similar, but there it's far more tricky. With G.fast, I could say it's a one-dimensional problem because there is no interference in between the line. The only thing you need to do is decide on the split upstream downstream. So there is one parameter, MDS as it's called in the standard, and you need to play with that parameter. With G.hn, as all lines are interfering, there is not only the split upstream downstream, but you also need to decide how you allocate that capacity to the different users by playing in the time domain and in the frequency domain. And that's far more complex. Another illustration of how CDTAs work in the field. So these are measurements or observations we did in a live network. So data is being collected by our Altiplano controller. For all G.fast DPUs, this is data for one DPU, a DPU with 16 users active. And basically what you're seeing here on the right, you see what is called the maximum MDS over 15-minute intervals. On the left, the minimum MDS. So MDS, again, is this parameter that determines the split between upstream and downstream. If you look at the figure on the right, you see that almost in every 15-minute interval, MDS was reaching its maximum value, what means that there was sufficient downstream traffic for making that change. with two exceptions in this example. On the left, you see that there are many intervals where the MDS reached its minimum value. In reality, it will probably, in a 15-minute interval, change many times in the full range. And so what we also observed here that is that there are more intervals where, or more 15-minute periods where the M reaches its maximum value. So no, I would say no surprise, because downloads are today more frequent than uploads. And what we also saw that when there were 8 GFast users active or more, that in nearly every interval MDS reaches its maximum value. So that for a twisted pair. Let's now have a look at the situation for coax. So here we have 3 choices. There is again G.fast, G.hn, and there is a newcomer, MoCA. MoCA is standardized by the MoCA Alliance. When we now compare, okay, all 3 technologies work point-to-point. G.hn and MoCA can be used point to multipoint. In terms of spectral bandwidth, MoCA is using a wider band, 500 megahertz, that can be flexibly allocated in between 1,400 and roughly 1,700 megahertz. All 3 technologies can coexist with TV services, but MoCA offers here more flexibility because you have different band allocation dependent on the use case. And if I say a TV, that can be, in case of MoCA, it can be terrestrial TV, it can be cable TV, it can also be satellite TV. Only the MoCA technology can coexist with DOCSIS, DOCSIS 3.0 and 3.1, 3.1 with some compromise in terms of maximum bandwidth usage. And if we look at maximum bit rates, I already mentioned tools for G.hn and GFast, and then we see that MoCA delivers 3.2 gigabit per second aggregate and up to 2.5 gigabit per second in each direction. So MoCA comes out as the technology that can deliver the highest bit rates and also as the only candidate that can coexist with DOCSIS. So what you see here are different band plan allocations of the MoCA technology, referred to as AA up to AE. So dependent on your use case, you can select one of the bands. For instance, on the top, you see allocations, frequency allocations that are compatible with terrestrial TV. If terrestrial TV goes up to roughly 350 megahertz, if you need more spectrum for the terrestrial TV, you use a higher MoCA band. If you need satellite TV, you choose the AAS. If you want to combine it with DOCSIS, you use AD or AE. So it illustrates the flexibility of the technology. Then if you have a look at bit rates as a function of length, so here we did the test. This was a coax cable of different lengths. There was no splitter inserted in this test. You see 3 bars, 3 colors at different loop lengths in the range 0 meter to 250 meters. These tests are with the AA band, the AA MoCA band. So the blue are the downstream bit rates, the orange the upstream, the upload rates, and then in gray you see what we achieved as aggregate capacity when we were sending traffic simultaneously in both directions. Well, in fact, to be a bit more precise, for the blue bar, so for the download test, what we did, we were sending large packets in downstream, and at the same time, we were sending small packets, 64-byte packets, I think, in the upstream direction to mimic acknowledgement. Same for the orange bars, we sent large packets in upstream, and we sent short packets in the opposite direction at half the frame rate. And so basically that you see here that up to 200 meters and even beyond, you get the full capacity with the AA band allocation. When we then repeat the test with the AD band, the situation is a bit different because the AD band is located much higher in the frequency, so it experiences more crosstalk. Not more crosstalk, more insertion loss. Now, coax is a very good medium. If we compare to twisted pair, for a given distance, you have much less attenuation. Still, at these high frequencies, the attenuation plays. But the MoCA standard has defined different, what is called power contours, different power levels. And then, so the left measurement was done with power contour 1. If we then activate a power amplifier that is integrated in the DPU and in the CPE, then we get the picture on the right where you see that the power contour 2 is largely, or in almost all cases, compensated for the losses that you experience at these high frequencies. We also did the speed test, two setups here. The top one is an iPerf test, an iPerf server, iPerf client. So we achieved 2.3 gigabit per second in both directions. And we repeated the test with an Ookla server and an Ookla client, and very similar results. One slide to illustrate how an operator could migrate from pure DOCSIS to MoCA technology. So on the left you have a building example, two users using DOCSIS technology. And then on the right there is one user remaining on DOCSIS. You introduce the MoCA DPU in the basement. You have a duplexer to combine the MoCA signal with the DOCSIS signal. And then another user got upgraded in this example to MoCA. And both can coexist peacefully in the building over the same coax wiring. And then in terms of solution offering, so we have our Altiplano controller. That's a unified management platform. So it's managing fiber to the home users, the MoCA users, and the GFast users, single pane of glass, as we call it. And okay, it's making use of intent-based networking to manage the network resources, to manage the services. We have zero-touch DPU installation. We have flow-through provisioning. So basically what it means, you take the DPU off the truck, you connect it, it gets automatically configured. And we make sure that the traffic is flowing through the OLT up to the DPU and through the DPU and to the CPEs. We have persistent PMA support, persistent management agent support, what allows you to configure the DPU even before it's installed or when it would be empowered. We have network views with dashboards with the most common and most important information. And alarm, of course, we are doing alarm analysis and performance monitoring. And we have the necessary support for software upgrades of DPU and CPE. So, to conclude, with our Gigabit Connect solution solves the MDU connectivity challenge. So we choose GFast for twisted pair because of best performance and because of guaranteed performance under coastal conditions. We have chosen MoCA access because of best performance on coax with 2 gigabit services in both directions, and as it can coexist with TV and DOCSIS. And okay, we have a uniform or a unified management offer and solution, single pane of glass, intent-based networking, so to make abstraction of the underlying technology and the complexity of the underlying technology. And that's basically it.
If there's one from the floor, oh, it looks like Manuel has one.
So is it on? Oh, no, thanks. Great talk. So one question, how do you power the DPU in this regard, in this case?
Mm-hmm. Different options. In case of GFast, you can do local powering. If local power is available, you can do reverse powering, where the CP is powering the DPU. In case of coax, you can use, again, local powering, or you can power it over the coax.
Okay, thanks.
Just real quick one. Oh, go ahead. We've got one.
Matthias from ABM. What is the, I mean, my understanding is that both solutions are already in the market, right? You can deploy this, and what is the percentage of G.fast and what is MoCA? You have a number on that one?
So both GFast technology and MoCA are in the market. So Nokia has a G-Fast solution since several years. For Mocha, Nokia is collaborating with Incoex. Incoex has Mocha solutions in the market today. You will see an example later this morning from Helge. We are now integrating the Incoex solution, the Mocha solution, into our overall solution, as I've shown, integrating with Altiplano, and it will soon become available as a solution. So I cannot yet tell you what the split is in terms of market. By the way, we also have operators, customers today that are using our G-Fast technology over coax. So that's possible as long as the coax is point-to-point. What we see is G-Fast, with G-Fast we are more addressing the telco operator market. With Mocha we are more addressing the cable operator market, the MSOs.
Thank you.
That was very good. It was a great way to open us up to the rest of the day. So let's give him a big hand. I would do that, but I'm going to film everyone clapping. So